Okay, another day, another few bits of soldering and what have you. Some things went well, some things went less bad. So I moved it all onto a prototype board, which is soldered. It's considerably more stable. I'm using the ESP32N with the Wi-Fi. I did make the mistake of mounting this too far to this end to get the USB in without bending it. You live and learn, but I'd already soldered all 38 pins when I discovered. So this prototype board's got two power buses, one along the top, VCC and ground, one along the bottom, VCC and ground. VCC is of course by convention positive, but there's nothing forcing you to make it positive. Then we've got this input which is 12 volts maximum and should be 12 volts. Appears to be reverse polarity protected, and there are two regulators. And what's interesting about the regulators is that they can be switched, so you can have them output to the VCC rail 12 volts, 5 volts or 3.3. Ergo, the top one I've set to 5 volts, pull the 5 volt rail, stick it in the 5 volts pin, V5. Should say 5V, but it's close enough. The blue wire is on ground, goes into the ground pin that's obscured by the brown wire. These 4 wires go to the motor driver, and running it originally I had the motor connected to the 5 volt rail, and this regulator was getting quite hot. So I didn't even bother looking what it's rated to. I just ordered some 7805 regulators and I got 10 for a fiver, so 50p a piece. For stability reasons, these like to have a 0.1 microfarad capacitor between the input and ground and the output and ground. I may need to have an electrolytic capacitor as well between the output and ground. The input appears to have these 100 microfarad 6.3 volt caps on anyway. That one for this rail, that one for this rail. So the software I've left alone, there's been some minor tweaks, but nothing serious. The only thing I've really done is add an indicator onto the remote application to show me the position so that I can see where it is. And it has proved useful already, because what I have found is that when I operate each band, it's very good to have a number to start from. So if I know what the required position is, I can dial that in and check the reception side, either side of where I am, to maximise it on the S meter, on the radio or on the SDR, whichever I'm using. And when I come to transmit, I can then watch the SWR meter and only have to move it in small amounts to optimise it. More on the SWR later, having some issues. So there's the board on that side. On the other side of it, some reasonable soldering. Yes, there's a bit of flux on it. That one went a bit wayward. These are connected along these rows, and those are connected along those rows. I did actually manage to short it out, so a slapped wrist for that. Fortunately, everything was short circuit protected. The motor driver, I ummed and ahed, should I take these off and solder them up, or should I hot glue them? Hot glue it is then. Okay, so this is the full circuit. Sorry for the horrendous drawing, it's not my forte. So this is the 12 volt socket, rather badly drawn, but the outside is the earth pin. And that goes to pin 33, which is ground on the ESP32. It does also go to ground on the regulators, I've not drawn it in. It also goes to the centre pin on my 7805. The input 12 volts goes to both regulators, and then there are these three push on, push off links that can set them. So regulator 1 is set to 5 volts, has a 100 microfarad cap at 6 volts and goes to pin 38, which is the 5 volt V in. Some boards say V in, some say 5 volts. You try that at your own risk, but 5 volts is adequate for the job. Second regulator is now not doing anything. That's the one that was getting hot. So this one's coming into the 7805, 0.1 microfarad decoupling on the input, 0.1 microfarad decoupling on the output, into the ULN2003 controller board and ultimately the stepper motor. And I changed the pin numbers for one simple reason. I soldered them in the wrong position. So it doesn't start at whatever pin it started at before. Anyway, the pin numbers are right for my sketch on my board, so double check please whether you're following this diagram or my software. I'm not going to change them in the software because if you follow the software it'll be right. Stepper motor with its little 5mm shaft. I didn't highlight it, but the coupler went straight onto the motor, but on the variable capacitor I had to put some insulating tape on the shaft to make it sit. It just wasn't worth making a fuss about. I also added an LED and a 220 ohm resistor across the 12 volt line so that I can see it from the house, probably. It's still not waterproof, so it's going to have to come in at night. So that's it. So let's have a look at the videos of the rest of it. Okay, so I've hot glued the connections into the motor controller because I don't want them coming loose while it's outdoors. Built on the prototype board, I've dispensed with the optical inputs for now. This has a DC jack that you can send a voltage into up to 12 volts. So I'm sending 12 volts in, and there are two power buses. The one on this side is 5 volts, and that's going into the 5 volt input on the ESP32. These are the two regulators for the two buses. One there, and a bit of smoothing. On this side, where have we gone? This one I've got the voltage set to 12 volts. And this is going into a 7805 regulator for the purpose of feeding the motor. So the motor is actually being fed from stabilised 5 volts. It's approximately an amp. It draws about 900 milliamps. This may be enough in the long run, but the motor's not normally on for very long. A couple of 0.1 microfarad decoupling capacitors. Nice bright red LED so I can tell that the 12 volt rail is active from a distance. 220 ohm resistor. And that's it really. So this is all going outdoors. So I've got some stuff to show you outdoors. Sorry about the wind chimes. Okay, so this loop is now 2.6 metres, which my calculation says correct. The coupling loop is 0.5 metres. I've had some issues with the connections on that, but hopefully everything is wire tied together now. The tape's still on, but I've wire tied it as well, so it shouldn't move around as much. And here's the motor control unit, exactly as it was. Here's the motor control unit, exactly as it was. And on the far side, I've now put the lid on to waterproof it. I've also put a switch on to disable one gag of the capacitor to reduce the capacitance to a maximum of 100 picofarads instead of 200. So it's not waterproof, it's not rain ready, but that's what we've got so far. So let's plug it in and test it. So welcome to my workshop. This is where all the craziness happens. It's also a conservatory. Let's go outside. Okay, so here's the finished MagLoop. Don't mind the wind chimes. Looks rude, doesn't it? So here's the MagLoop. Here's the circuit board with its LED on. And there's the variable capacitors and motor. The switch allows me to switch off one bank of the capacitor to get the to switch it between 100 pf maximum and 200 pf maximum. And the wire goes to a little power supply inside the house. So that's it in situ. Still got some work to do on it. The SWR is horrendous, but we shall see. We shall see what happens. This board has got 3 green LEDs on as well that you can't see normally. It's quite windy, so that's why I've got an elastic band around it. As with everything I do, it's a temporary installation. So, right, back inside. So, the antenna is not completed, but the next stage is completed. So what's the SWR like? Get this nice dip at about 18 megahertz, 18.1 megahertz. And as you can see, the SWR is awful. That's 7.4. So what I need to do now is to try tuning it. Now I've got both capacitors engaged on the switch, and the capacitor is fully open. So that's at the fully open setting. I'm going to take it to fully closed. Now you won't see it in real time. Take it to halfway. So we rescan it halfway. And now at 10 megahertz. So that's interesting. Not what I want, but it's interesting. So take it all the way close, so we're increasing it to maximum capacitance. Okay, so that's putting the, I was going to say peak, but it's not, it's a drop. There, at 7.38 megahertz. I've got to admit I'm confused by this. So it's not going to go all the way down to 7 megahertz for starters. So at 709, it's going to have an SWR 19.6. It's not good, is it? 12 megahertz, it's 10 megahertz, the SWR is 12. (21 megahertz, it's around 10. So I'm not really sure what's going on here. Let's see if I can run it on here. If I just tune it down slightly, I've got this drop here at 7.3 megahertz. But if I take it up just a position or two, the dip comes up. So if I've got a few clicks down and the dip has almost disappeared. It's there now. It's still at the same frequency though. So that was at 0. This is at 20. So it's only moved a little bit. So you can't say I've now got numbers that tell me how far on it is. And that goes from 0 to 270 to suit my capacitor. So they're not just moved, but it's hardly moved at all. At 50. This is at 80. The notch is moving, which is what you'd expect it to do. This is at 110. It's hardly moved. So this is at 130, approximately the halfway mark. We're still only up to 10 megahertz. So I think I followed the calculations. This is at 160. I followed the calculations to make it resonant at 15 metres, 20 metres and 40 metres. I didn't bother with 80 metres, which is the only other band I've got on this Xiegu G1M radio. And he said for 2.6 metre loop, with a 0.52 coupling, I'm going to get my spreadsheet up and show you. So here are my calculations. So So we've got the frequency, the resonant frequency, the voltage of the capacitor, the value of the capacitor, the bandwidth, the efficiency, and Q. So I don't know how you have a Q of 0.38, a Q of 1169 at 0.38 efficiency. I can only assume that it's all lost, basically. So 7 megahertz. So we've got 2.61 circumference, which is approximately a metre diameter, just over a metre diameter. It says 0.83 to be fair. I don't agree with that. No, 0.83 times 3.142. Okay, and then a coupling loop of 0.52 metres, which it's around that figure, it's about 0.5. So on 7 megahertz, we were getting a dip. So allegedly there's 900 volts on the capacitor. It should be at 217 picofarads, which would be slightly beyond what the capacitor is, because it's 2 times 100 pf, but then you've got some capacity in the system as well. And that's very inefficient. Is that what's giving me a bad SWR? And then at 14 megahertz, 20 meters, the efficiency is 32%. So you would imagine it would tune. "21 megahertz is 67% efficient. So you would imagine a really good SWR at 21 megahertz. Now the capacitor only needs to be 18. Now I've got the capacitor set to 200 picofarads maximum at the moment. So what I'm going to do, I'm going to go outside and switch it over. Okay, so turn the capacitor down. I'm going to set it to minimum capacitance by fully opening it. So it's closed at 0, and at 270 it's fully open. It's for maximum capacitance. Sorry, it's minimum. It's full capacitance at 0, it's minimum capacitance at 270. Behold, a dip at 21.59 megahertz, but it's still an SWR of 4.59. 4.539. So if I try to tune this, I put a marker on the VNA at 14 megahertz. So 14 megahertz, I'm now going to tune it on the VNA and then I'll put it on the screen. So I need to increase the capacitance. See, now it's going along beautifully. And it goes to 14 megahertz. It's bouncing up and down as the wind is going. So there we go. So 14 megahertz. And now got an SWR of 5. It's like the impedance is way out, 70.9 ohms. So what happens if I tune it more? Let me tune it further down, further down, further down. I can tell the VNA is picking up the radiation from the motor. So at 9.9 megahertz, it's saying it's 42 ohms. But the SWR is 9. There's something very confusing about all this, and I'm going to have to do some research and ask around on the forums, because I'll be honest, it's beyond my knowledge. So the important thing is, it works. We can remote it from the house. We've got the loop built. It's tuning something of this frequency range. So if you choose down to 10 megahertz and then up, so this is the minimum capacitance, it's just one capacitor, fully open. It's about 10 picofarads, I can tell you that off the top. So that will tune 21 megahertz-ish, but the SWR is awful. That's why they need to experiment with different coupling loops. I don't see how I can change the main loop much because it's doing what I'm asking it to. I'm not bothered about 10 metres because I don't have 10 metres on my rig. I can receive it, and I can receive it regardless of the SWR. But I want to transmit on it. Well, I don't want to transmit on 10 metres because I can't. But I want to transmit on 21 megahertz, 15 metres, 20 metres, 40 metres. I want to transmit on. But the SWR is horrible. I do think it's a coupling loop. Is it because I'm connecting the inner and the outer of the coupling loop together? Does that affect it? I don't know. I really don't know. I'm baffled. But the electronics is working, the mechanics is working, and we've got a MagLoop antenna. We've got an Arduino-based controller. Okay, it's an ESP32. So I've sort of achieved the objective. I've built the development system, if you will. I've got something that I can test the antenna side on now. I'll go further. Oh, I wanted to show you something, just a second. So what I did do a bit of transmitting this afternoon. Because of the atrocious SWR, what I did, I ran it through the ATU. And I tried it on 20 metres, and this was the results, not ideal times, but my tester, my website, my DX display this afternoon showed that 20 metres was the predominant activity. So I threw it into the ATU, and in space of about 15 minutes, 20 minutes, I got 1, 2, 3, 4, 5 contacts on FTAs. Now FTAs is not my strong thing, but these were outbound. These were people who were logging it to the tracker on PSK Reporter, but they weren't contacting me back. So either I couldn't hear them, I'd have to go through the logs, or they were working, but one was in Croatia, one's in Croatia, I didn't notice that one at the time. It looks like Germany. One in Norway, one in Sweden, one in Finland. So it sort of works. It's not ideal. I tried to do some damage on one of the other bands, but I didn't actually manage to succeed. So I've still got a long way to go with the antenna itself. But as the controller functions. Just need to decide now what other functionality I need to add in. Maybe the capacitor I've got is faulty. It's post-war, so it's got to be 60, 70 years old. Maybe it's leaky. Maybe it's got resistive components. Maybe the way I've got it connected has introduced an inductive component. I've used short, thick copper wires from Twin and Earth, that are about 1.5 mil diameter, to connect to the capacitor. I'm baffled. It's not often I'm baffled, but I need to do some research. So this is it for part 3. So I welcome your thoughts on why my SWR is cuckoo. I've used RG58 for the coupling loop. I've used RG213 for the main loop. Yes, I've got a bit of metal going through the middle of it. It's not ideal. What am I doing wrong? Please tell me in the comments. Hope you enjoyed this series so far. I don't intend to extend it indefinitely. I'd really like to get to the point where we resolve this and I can just give you a short one to say it's done. So please like and subscribe, tell your mates about it, share it on social media. We'll see what happens next. But I do like my ESP32 controller. I now need to build it into a case, and probably I've got another capacitor that's identical. So the finished product is probably going to end up with them all inside a big box and be waterproof. I've no idea how I'm going to manage that. I just wanted to develop the software and the hardware. So, have fun with this. Hope you try and build one. I'll put the latest version of the code on Git. And good luck and best 73s. That's it for now. I'm going to go and get on my motorbike now and try and enjoy the rest of my holiday.